Right now, as you're watching this video, something is happening directly behind the sun that we can't see at all. An ancient visitor 10 billion years old from another star system is at its closest point to our star, trapped in a perfect cosmic blind spot. Before vanishing, it did the unthinkable. It blasted streams of material toward the sun, defying physics. And now in 8 days of total silence, it's going through the most intense moment of its journey, and we're completely blind. Scientists are holding their breath until December to see what or who emerges from the other side. If you're feeling this suffocating curiosity too, and want to be the first to know when the mystery breaks, smash that like and subscribe button right now. We're tracking every twist. Something is happening that the human eye can't see. Right now, as you're reading these words, an object from another star system is making its fateful passage directly behind our sun, and we have no idea what's happening to it. How is that possible? In an era where humanity has reached the peak of technological arrogance, where we can photograph black holes 55 million light years away, track car-sized asteroids brushing past Earth from millions of miles, how can something tangible, a physical object, be completely invisible to us just because it's hiding behind our own star? Today is October 29th, 2025, and somewhere out there on the far side of the sun, locked in a brutal cosmic blind spot that renders every Earth-based telescope, from mountaintop observatories in Chile to billion-dollar orbital satellites, utterly useless, an interstellar visitor named 3IATLAS is experiencing the most intense moment in its estimated 10 billion year existence. It's not just passing through. It's doing something mysterious, something that's kept scientists worldwide sleepless, obsessively rechecking calculations, waiting in desperation until December. That's when this ancient wanderer finally emerges from behind our star's blinding plasma curtain and reveals what the sun did to it, or perhaps what it did to the sun. But here's the real kicker, the irony that makes this moment so maddening for astronomers and so thrilling in a nervous way for anyone who gets what's at stake. The moment 3IATLAS reaches its closest approach to the sun, what scientists call perihelion, happens to fall at the worst possible time for observation. Thanks to a random cosmic coincidence, an orbital mechanics setup that feels almost orchestrated, this interstellar object hits its closest point to our star, while sitting directly behind the sun from Earth's perspective. The phenomenon is known in astronomy by the cold term solar conjunction. And for 8 long days, from October 21st until today, October 29th, 3IATLAS has been nearly invisible to us. Not because it's too faint, not because it's too far. It's invisible because the sun's unbearable glare creates an observational dead zone, an absolute blind spot no human technology can overcome. Think about what that really means. We've been waiting for this moment for months, ever since its first anomalies were recorded. Observatories worldwide planned coordinated campaigns in detail. Precious telescope time on billion-dollar instruments was allocated, debated, and locked in. Scientists prepped spectrometers, calibrated them to perfection to capture the faint chemical signatures they believed would only appear when extreme solar heat forces ancient volatiles off the comet's surface. And then right when all that preparation was supposed to pay off, right when 3IATLAS is enduring temperatures high enough to explosively vent its billion-year-old CO2 ices into space, we're forced to look away. It's a cruel irony. It's like watching a suspenseful mystery thriller, tension choking you, and the screen goes black right at the big reveal, right as the killer's about to unmask. All we have left is the hum of machines and our own imagination. The perihelion distance itself tells you something critical about what's happening behind the sun's curtain right now. 3IATLAS isn't a reckless comet skimming the sun like some past daredevils that dove in and vaporized. No, it passes at a calculated 1.36 AU, about 203 million kilometers. For scale, that's roughly the distance between Earth and Mars when they're on opposite sides of the sun. In fact, right now it's farther from the sun than Earth is. So we're not talking about an object that will instantly melt or shatter from proximity. Instead, we're talking about an environment intense enough, a radiation furnace strong enough to dramatically accelerate any processes already brewing inside it. Processes that began as 3IATLAS fell deeper into the sun's gravity well over the past year. Processes that made scientists frown and question. Before the comet vanished behind the sun last week, astronomers saw something that shouldn't happen. Comets by the textbook are supposed to follow predictable rules. As they approach the sun, solar radiation heats their surface, sublimating ices, turning them directly from solid to gas without a liquid phase. This outgassing, this material eruption, creates a characteristic tail, and the golden rule is that tail always points away from the sun. It's pushed by solar wind and radiation pressure like a cosmic windsock, always showing the direction opposite the star. That's basic comet physics. That's what we see every time a comet enters the inner solar system. Except 3IATLAS, this interstellar visitor, refused to follow the script. Throughout July and August 2025, multiple observatories operating independently detected something anomalous, something almost heretical. 3IATLAS was producing gas and dust streams as expected, but instead of forming the anticipated anti-sunward tail, it created a smoke plume, a bright streak pointing straight at the sun. Pause and think how backwards that is. It's like seeing smoke from a fire blowing into the wind instead of away. Like watching water flow uphill defying gravity. These observations weren't a fluke. They were confirmed by the most reputable sources on the planet. The Hubble Space Telescope, our trusted eye in space, captured the phenomenon in crisp images. The European Southern Observatory's Very Large Telescope VLT in Chile, one of the world's most powerful optical telescope arrays, confirmed it with spectral data. This wasn't equipment failure or observational error. 3IATLAS was genuinely behaving in a way that contradicted everything we thought we understood about comet mechanics. Of course, the scientific community, which doesn't like unexplained mysteries, quickly offered explanations. The leading and most reasonable hypothesis is that the sunward jets were created by preferential scattering from the comet's illuminated hemisphere as it rotated. Basically, the scenario is this: imagine the comet nucleus rotating. Like Earth, it has a spin axis. Suppose that axis is tilted in a particular way, and on its surface there's a particularly active region, maybe an ice crater, an exposed patch of volatile ice like CO2. Due to the tilt, this active region spends more time facing the sun than other parts of the comet. When it heats up, it produces a strong directed outburst of gas and dust. Now, add the viewing angle. If the comet's rotation timing the jet's direction and our line of sight from Earth all aligned perfectly, we could see those jets appearing to point toward the sun from our perspective, though in reality the gas and dust, once a few colored off the surface, are immediately bent and pushed outward by radiation pressure. Essentially, it's an optical illusion, a trick of perspective created by rotation and observational geometry. Overall, it's a perfectly reasonable explanation. It doesn't violate known physics. It preserves cosmic order. However, it also requires a very specific set of conditions, a coincidence of multiple factors: spin, axis, hotspot, location, viewing angle, to produce exactly what we observed. And that's when a vague unease, a tiny doubt, starts creeping into some observers' minds. How many times can something require a very specific, very coincidental set of conditions before we start wondering if we're witnessing something other than random chance? By late August, as if to calm those concerns, the sunward jets vanished. They shifted to a more conventional anti-sunward tail structure, like a rebellious child finally following the rules. The Nordic Optical Telescope on La Palma in the Canary Islands captured the morphological shift into tail. The cause of the anomalous jet seemed resolved, or at least self-corrected, as 3IATLAS continued its approach to the sun. The comet started looking more like a comet, but the memory of those reverse jets lingered. It lived in published scientific papers, and it lived in the minds of researchers who'd spent months tracking the object. Because once something has clearly exceeded your expectations, even if it later behaves normally, you watch it more closely. You start wondering what else it might do outside the rules. Then came the Mars flyby on October 3rd, another notable event. 3IATLAS passed the red planet at just 0.19 AU, about 28 million kilometers. This was a golden opportunity. 3 orbiters had a once-in-history chance to observe an interstellar object from a completely different perspective than Earth. The Mars Reconnaissance Orbiter, MRO. Europe's Mars Express and other spacecraft were repositioned, their cameras pointed into deep space instead of down at the red surface below. They were tasked with capturing images and data during this fleeting encounter. While some images have been released showing the comet's head and tail from Mars's viewpoint, confirming it was still highly active, persistent claims, whispers in amateur astronomy communities and online platforms like Reddit say Not all images, especially the highest resolution ones from MRO's HiRISE camera, were released immediately. NASA and the European Space Agency ESA issued official statements affirming all images are following standard processing and calibration protocols and nothing is being hidden. However, some independent observers spending nights analyzing every pixel of released data claim the Mars encounter. Images revealed details, possibly minor structural anomalies in the comet's head that needed further analysis, needed explanation before public release. Whether those claims hold water, we can't know for sure. Delays in scientific data release are normal, but in the context of an object that already challenged physics, that delay takes on a different meaning. It fuels suspicion. What we know for certain is that by October 21st, the angular separation between 3IATLAS and the Sun as seen from Earth had shrunk to unobservable levels. The comet had disappeared behind our star's glare, entering a week-long blackout. A radio silence ending today, October 29th, as it reaches perihelion. Right now, at this very moment, 3IATLAS is at its closest point to the Sun in its entire journey. It's moving at a terrifying 68 km over 240,000 km/h. It's experiencing the strongest gravitational acceleration and most intense heating of its entire passage through our solar system. And we, with all our technology, can't see it. Every major Earth-based observatory is staring uselessly at the sky waiting. The GAOIS 19 satellite, one of NOAA's weather satellites, capable of detecting near-Sun objects in daylight, but only under the most ideal conditions and only for sufficiently bright objects. 3A. Atlas, even at perihelion with maximum enhanced outgassing, may not be bright enough or favorably positioned for that extremely limited observation. The Mars orbiters, our last hope, are now too far and at an unfavorable angle to provide any useful data. We're truly blind. For these 8 days, the most studied, most anticipated interstellar object in recent astronomical history has been occulted from human view. And this happens at the exact time when the most dramatic changes, the deepest structural and activity transformations are occurring. That's what makes today, October 29, 2025, insane for scientists and unbelievably compelling for anyone following this story. We know something critically important is happening. We know solar radiation in all its power is bombarding 3IATLAS with enough energy to cause violent outgassing, possibly peeling away surface layers. We know its velocity is peaking. We know solar tidal forces, though not strong enough to tear it apart at this distance, are certainly stressing its potentially unstable internal structure. We know all this is happening, but we can't see. We can't measure. We can't confirm what computer models predict will happen versus what actually does. We're forced to wait. We have to wait until mid-December when 3IATLAS moves far enough from the Sun's glare to once again be observable in the pre-dawn sky. Only then will we know. Only then will we have answers. Is it still intact? Has its activity increased tenfold or died out? Has its already strange chemical composition changed under perihelion's assault? Does its orbit still follow pure gravity, or does it show signs of non-gravitational forces? Mysterious thrusts from outgassing that could reveal more about its nature. If you, like me, find yourself gripped by this cosmic mystery, if you realize that right now at this moment something profound, something that could change our understanding of the universe is happening in a place we can't see, go ahead and hit that like button. Leave a comment and honestly tell me, do you think 3IATLAS will look the same when it reemerges in December's? Just a space rock that had a hot day? Or do you think the Sun might have changed it in ways we can't predict? Let me know where you're watching from, because this is a global moment. Somewhere in Australia, someone's watching this at dawn, gearing up for a new day. In California, someone's tracking the night, looking up at the sky. And all of us, wherever we are staring at the same sun. A sun hiding something we desperately want to see. That shared curiosity crossing time zones and continents is what makes moments like this matter, even when we can't fully explain why. The question driving everything else, the question hanging in the silent air of telescope control rooms, comes naturally from understanding what we currently cannot observe. Exactly what is Comet 3IATLAS doing behind the Sun right now? And what will it reveal about itself when it emerges? Before 3IATLAS vanished behind the solar curtain, before it entered the observational darkness we're experiencing, it gave us previews of its strange phenomena. Those behaviors, as mentioned, still don't fully fit standard comet physics. And understanding exactly what happened in the weeks leading to conjunction is essential to understanding why scientists are so eager, and perhaps a bit anxious to see what this object looks like when it reappears. Let me explain more clearly what a comet is supposed to do, because the stark contrast between normal expected behavior and what 3IATLAS actually did is where the real mystery lies. When any comet approaches the sun, solar radiation gets to work. It heats the surface. Most comets are essentially dirty snowballs, a messy mix of water, ice frozen carbon dioxide, dry ice frozen methane ammonia, and countless silicate dust grains all bound in a loose porous structure. As temperature rises, they don't melt into liquid like Earth ice. In space's vacuum, they sublimate, going straight from solid to gas. This process accelerates, becoming more violent as the comet nears the sun. This outgassing, this gas eruption, carries trapped dust grains, forming the visible outer shell we call the coma. The fuzzy gas and dust cloud enveloping the comet nucleus. Then comes the tail. And really it's tails, plural. Comets typically develop two distinct tails as they approach the sun, and they're different in nature. The dust tail is made of small, heavier dust particles released during sublimation. These particles, once freed, retain some of the comet's orbital momentum. As a result, the dust tail often curves slightly, following the comet's path. The second tail is the ion tail, or gas-rich plasma tail. This is made of gas molecules ionized by the sun's ultraviolet radiation, stripped of electrons, becoming charged. Once charged, they're completely controlled by the solar wind. The solar wind is a constant stream of charged particles flowing from the sun at terrifying speeds, about 400 km/s. This ion tail is blown violently outward and always points directly away from the sun, regardless of the comet's direction of motion. Always. That's the basic rule. Comet tails point straight away from the sun. Radiation pressure and solar wind push material into space. This is so reliable you could use a comet tail as a compass in the solar system. The opposite of the tail's direction is where you'll find the sun. In centuries of comet observation across thousands of recorded comets in human history, this principle has always held true, until 3IATLAS decided to complicate things. In July 2025, while 3IATLAS was still far enough from the sun to be clearly visible from Earth, astronomers using the Hubble Space Telescope conducted a series of observations, taking detailed images to track activity levels and any structural changes. What they captured when the first images beamed back to the Space Telescope Science Institute in Baltimore was immediately flagged as anomalous. 3IATLAS was producing a narrow, bright material stream, but instead of escaping away from the sun as every theory and prior observation predicted, the stream pointed straight at the sun. Not at a small angle, not an ambiguity easily dismissed by observational geometry. Straight at the sun. Hubble's images were crisp enough, detailed enough to show the unmistakable direction. In Chile, the European Southern Observatory's very large telescope, also tracking the object, confirmed the same phenomenon. Multiple observatories, multiple instruments, multiple observation days throughout July and early August, all showing the same impossibility, a sunward-pointing jet. The scientific papers rushed out on these observations were very careful in their wording. Science doesn't like the word impossible. They described the feature as a sunward-pointing feature, and noted it represents an unusual morphology for a cometary coma. That's scholarly speak for, this shouldn't happen and we need to figure out why. The papers explored several potential explanations. As mentioned, the leading hypothesis involves the comet's spin axis and the location of active sublimation regions on its surface. Here's the detailed version of that hypothesis. Imagine 3IATLAS rotating. Like Earth, it has a spin axis. Suppose that axis is tilted in a particular way, and on its surface there's a particularly active region, maybe an ice crater, an exposed patch of volatile ice like CO2. Due to the tilt, this active region spends more time facing the sun than other parts of the comet. When it heats up, it produces a strong directed outburst of gas and dust. Now, add the viewing angle. If the comet's rotation timing the jet's direction and our line of sight from Earth all align perfectly, we could see those jets appearing to point toward the sun from our perspective, though in reality the gas and dust, once a few kilometers off the surface, are immediately bent and pushed outward by radiation pressure. Essentially, it's an optical illusion, a trick of perspective created by rotation and observational geometry. This explanation has precedent. Other comets in our solar system have shown similar jets deflected by localized active regions. Comet C 2014 UN271, also known as Bernardinelli-Bernstein, another giant comet, also displayed asymmetric outgassing, creating jets oriented at unusual angles to the Sun. So the phenomenon of localized jets from rotating nuclei isn't unprecedented. What stands out, what makes scientists pause and think in the case of 3IATLAS, is the duration and prominence of that sunward orientation. It wasn't a fleeting phenomenon lasting just a few hours in a comet rotation cycle. It persisted clear and stable across multiple observation sessions spanning weeks. This means the coincidence of spin axis and viewing angle had to be maintained perfectly over an extended period. Then in late August, something shifted. The Nordic Optical Telescope, a 2.5-meter scope at the Roque de los Muchachos Observatory on La Palma, captured images showing 3IATLAS's jets finally surrendered. They transitioned to a more conventional anti-sunward tail. The reverse jets vanished or were overwhelmed, replaced by the expected faint, elongated tail pointing straight away from the Sun. Whatever bizarre conditions created the anomalous shape in July and early August seemed to self-resolve. The comet started behaving normally. You might think that settles it. Mystery solved, right? Just an unusual but explainable rotation effect that normalized as the comet's orientation to the Sun changed along its orbit. And for most scientists in the mainstream community, that's essentially the conclusion. The sunward jets were interesting, a noteworthy footnote in the academic record, but ultimately fit known physics when you account for the complexities of rotation and observational geometry. But there's a reason, a psychological and perhaps scientific reason, this specific detail refuses to fade into the background of the 3IATLAS story. Because the sunward jets did happen. Because for weeks this interstellar visitor displayed behavior requiring specific, somewhat improbable conditions to explain with standard comet physics. Because even with those reasonable explanations, some observers still have an uneasy feeling, a sense that we're watching an object not entirely following expected rules. Consider another explanation, one hovering on the fringes of mainstream scientific discussion, one no serious scientist would dare put in a paper. What if those sunward jets weren't an optical illusion? What if they represented genuine directed outgassing, possibly from vents or openings designed to channel material toward the Sun for reasons unrelated to passive sublimation? Such a scenario would require some kind of internal structure, an organized structure, even possibly deliberate geometry to direct gas in specific directions. Such a scenario, of course, would instantly transform 3IATLAS from a natural comet, an ancient space rock, into something entirely different. Something engineered, something with intent behind its design. A probe. Before you dismiss that as pure sci-fi, understand I'm not endorsing this interpretation. I'm explaining why those sunward jets, even with perfectly reasonable and valid scientific explanations, continue to fuel speculation, continue to be a key part of the mystery. Because once you've seen an interstellar object do something requiring you to invoke special conditions, coincidences to explain it, maintaining absolute certainty about what you're seeing becomes harder. Doubt creeps in. Not scientific doubt in the rigorous, healthy sense, but doubt in the sense of what else might this object do to surprise us? What else might we discover that doesn't fit the model? And it turns out we did discover more. Observations from the Very Large Telescope didn't just confirm the sunward jets. They provided detailed spectral data. Spectroscopy is key. It reveals what materials are actually in those jets. And this is where the chemical story of 3IATLAS gets truly strange, but we'll dive deeper into that shortly. For now, the takeaway is those jets weren't just visually unusual. They carried distinctive chemical signatures that forced astrochemists to ask tough questions about what 3IATLAS is made of, and where it came from. By September, as the sunward jets faded and transitioned to a conventional anti-sunward tail, 3IATLAS was accelerating, bulleting toward its October 3rd Mars encounter and late October perihelion. The morphological anomaly seemed resolved. Scientists could breathe a sigh of relief, believing the comet was behaving predictably. But that sense of predictability was about to be challenged again. This time not by its tail shape, but by its chemistry, a chemistry that turned out to be profoundly different from anything we'd seen before. not just in solar system comets, but even compared to the only other well-studied interstellar comet 2I Borisov. The sunward jets were the first sign Atlas 3I would defy expectations. And as observations continued, the chemical evidence mounted, revealing an object potentially far stranger than its initial appearance suggested. Every comet is a time capsule. That's not poetic hyperbole to make science exciting. It's literal scientific truth. Comets form in the cold outer regions of star systems where temperatures are low enough for volatile materials, like water, carbon dioxide, methane, and ammonia, to freeze and accumulate into larger bodies. Once formed, these icy bodies remain nearly unchanged for billions of years, as long as they stay in the cold dark, far from their parent star's radiation. They preserve, like a specimen in a freezer, the chemical composition of the primordial stellar nebula they formed in. They're a frozen record of the conditions that existed when their star system was young. When we analyze a comet's chemistry, we're essentially reading a message from the distant past. We're learning what materials were present in that patch of space billions of years ago. So when 3IATLAS entered our solar system from interstellar space, scientists saw an extraordinary opportunity. This wasn't a comet formed in our solar system. This wasn't a member of our Oort cloud or Kuiper belt. This was an object formed around a completely different star, possibly 10 billion years ago, based on initial age estimates from its chemistry. An object that had been wandering the galaxy ever since a cosmic orphan. Analyzing its chemistry would reveal something about the conditions in that ancient distant star system. It would tell us whether the materials that built our planets and possibly life are unique or common across the galaxy. It would help us understand the diversity of planet-forming environments. That's why observatories worldwide from ground to space devoted precious time to 3IATLAS's spectroscopy. Spectroscopy, as mentioned, is the technique of splitting an object's light into its component wavelengths, like a prism creating a rainbow. By analyzing which specific wavelengths are absorbed or emitted by materials in the comet's coma, scientists can identify exactly what chemicals are present. Different molecules absorb and emit light at characteristic wavelengths, creating unique chemical fingerprints. It's detective work at the atomic level. And for 3IATLAS, the results were immediately bizarre. The first big surprise came from the Very Large Telescope VLT in Chile in late 2024 and early 2025. While 3IATLAS was still far from the Sun but showing signs of activity, astronomers using VLT's UVES spectrograph detected atomic nickel in the comet's dust cloud. Let's be clear, not nickel compounds, not nickel locked in dust grains. Atomic nickel vapor, individual nickel atoms floating freely in space around the comet nucleus. The detection was clear. Nickel has a very distinctive, strong spectral signature, and VLT's instruments captured it sharply. The emission rate was measured at roughly 4.6 grams per second. That number sounds tiny, but for atomic metal vapor released from a comet at that distance, it's extraordinary. Why is this strange? Because atomic nickel, by our understanding, shouldn't be there. Or more precisely, it shouldn't be there alone. In the universe, nickel usually comes with iron. Both heavy metals are formed in the same stellar nucleosynthesis processes inside stars and supernovae. So they tend to appear in roughly equal amounts in cosmic objects like meteorites. The rule of thumb is where there's nickel, you'll see iron right beside it in the spectrum. But VLT observations showed something baffling. Nickel was present, but there was no corresponding iron signature. 3IATLAS was producing nickel vapor without iron vapor. It was violating the expected chemical relationship these metals usually maintain. The scientific papers documenting this discovery struggle to explain the implications. One possibility is that 3IATLAS's formation environment, that distant stellar nebula, somehow preferentially incorporated nickel over iron into its ices. Perhaps due to the specific chemistry of the parent nebula. Different stars produce different element ratios depending on mass, age, and initial composition. Maybe 3IATLAS formed in a region unusually rich in nickel relative to iron. This is possible, but it requires fairly special, fairly rare conditions. Another possibility is that nickel-bearing compounds on the comet's surface are for some reason more volatile, more easily released by the weak solar heating at that distance than iron-bearing compounds. This creates a temporary abundance of nickel vapor that doesn't reflect the comet's overall composition. But this requires nickel to be in a much more volatile chemical form than iron, which isn't typical for these metals. And then there's the third possibility. One no mainstream scientific paper wants to mention directly, but it hovers around the edges of every discussion and conference-side conversations. What if that nickel isn't natural at all? What if it's there because 3IATLAS isn't entirely natural? Nickel is a common, actually critical component in human-made alloys, especially stainless steel and superalloys. It's used for structural applications because of its strength, corrosion resistance, and ability to withstand extreme temperatures. If you in advanced civilization were going to build something that needed to survive the harsh conditions of interstellar space for millions, even billions of years, nickel-based alloys would be an excellent choice. The presence of nickel vapor without iron in this scenario could indicate that the sublimating or sputtering surface material isn't from a primordial ice rock, but from an engineered object, a metallic shell. I want to be clear, this is speculation. It's not the conclusion the scientific papers reach. They're still working within the framework of natural explanations. But the speculation exists because the nickel without iron detection is genuinely anomalous, and because the simplest natural explanations require invoking special conditions. When something requires special conditions to explain naturally, but fits easily with an artificial explanation, that's when speculation gets attention even from those who understand the importance of not jumping to conclusions. The second major chemical anomaly involves carbon dioxide or CO2. NASA's James Webb Space Telescope JWST, the premier infrared observatory launched in 2021, was tasked with analyzing 3IATLAS's composition with its ultra-sensitive infrared spectrometers. Infrared is ideal for detecting molecules like carbon dioxide and water, as they have strong absorption features in infrared wavelengths. When JWST turned its instruments on 3IATLAS, the results were immediate and staggering. 3IATLAS is rich in carbon dioxide. Extremely rich. The ratio of carbon dioxide CO2 to water H2O in the comet's outgassing was measured at roughly 8:1. That means for every one water molecule released, 8 carbon dioxide molecules were released. This is the complete opposite of what we typically see in solar system comets. Most of our comets from the Oort cloud or Kuiper belt are water-dominated, often by a wide margin. A 1:1 ratio, or even 10. 1 favoring water is common. Comet Halley, perhaps the most famous in history, had about 3 times more water than carbon dioxide. Comet Hale-Bopp, one of the 20th century's brightest, showed similar water dominance. Even 2I Borisov, the first interstellar comet we studied in detail in 2019, had more water than carbon dioxide. But 3IATLAS is mostly carbon dioxide. And this tells us something profound about where it formed. Carbon dioxide dry ice is much more volatile than water ice. This means it sublimates, turns to gas at much lower temperatures than water. In the outer regions of a star system where temperatures are extremely cold, both carbon dioxide and water can remain frozen. But in regions a bit closer to the star where temperatures are slightly warmer, but still very cold, carbon dioxide will sublimate while water ice remains solid. What does that mean? It means a carbon dioxide-rich comet like 3IATLAS most likely formed in the extremely cold outermost regions of its parent star system, possibly beyond the equivalent of our Kuiper belt, in regions so distant that carbon dioxide was the dominant ice, not water. This implies 3IATLAS preserves the chemistry of a very cold, very distant formation environment. It's a messenger from the frozen edge of another solar system, one possibly much older and colder than ours when our comets formed. The 8:1 ratio, like the nickel, isn't impossible to explain naturally. It fits known physics. But it's anomalous enough that every astronomer who looked at JWST's data took note. It marks 3IATLAS as chemically distinct from nearly every other comet we've studied, and the third chemical anomaly also involving water, but in an unexpected context. NASA's Swift Observatory, a space telescope originally designed to detect high-energy phenomena like gamma-ray bursts, but also equipped with instruments especially in ultraviolet to observe comets, detected hydroxyl OH, emission from 3IATLAS while the comet was still very far from the Sun. Hydroxyl OH is a direct byproduct of water sublimation. When water molecules H2O are released from the comet and exposed to solar ultraviolet radiation, they're photodissociated, broken apart. They split into hydrogen H and hydroxyl OH, so detecting hydroxyl is essentially detecting water activity indirectly. What makes this detection significant is the distance at which it occurred. 3IATLAS was producing water vapor via the hydroxyl signature well beyond the so-called snow line, the point where we typically see water activity begin in solar system comets. Most of our comets don't start releasing significant water until they're within about 3 astronomical units AU of the Sun. That's where solar heating is strong enough to efficiently sublimate water ice. But Swift detected water activity from 3IATLAS at significantly greater distances. What does that suggest? It suggests the comet's internal structure is different from typical comets. It may be more porous, allowing solar heat to penetrate deeper and sublimate buried ice earlier. It may have water ice intricately mixed with more volatile materials like carbon dioxide, which we know is true. As carbon dioxide sublimates at greater distances, it disrupts the surrounding structure and exposes water ice, which then begins to sublimate too. Or its surface may have very low thermal inertia, meaning it heats up rapidly even under weak sunlight and efficiently conducts heat inward. Again, we see a pattern. There are natural explanations for this behavior. But again, those explanations require 3IATLAS to have slightly unusual, slightly special structural characteristics compared to a typical comet. The common thread in all these chemical observations, nickel without iron, CO2 dominance, early water activity, is that 3IATLAS is always anomalous. Not impossible, not unexplainable, but always outside the normal range. Each individual anomaly can be explained with a special natural scenario, but combined they paint a picture of an object that doesn't quite fit our existing categories. And there's one more piece of this complex chemical puzzle worth highlighting. This piece ties directly to the questions that will be answered hopefully when 3IATLAS reemerges from behind the Sun in December. Scientists using data from JWST and other observatories have been carefully tracking how the comet's chemical activity changes as it approaches the Sun. Specifically, they've been monitoring the carbon dioxide to water ratio, that 8:1, to see if it holds steady or shifts as temperatures rise. This is a critical test. If the ratio changes significantly as the comet heats up, it tells us the comet's surface layers are chemically different from its interior, like an onion with different compositional layers. The outer layer might be CO2 rich, but deeper layers more water rich. If the ratio stays constant even as the comet heats, it suggests the comet is relatively homogeneous throughout its structure. It's well mixed from core to surface. Before the October conjunction, the ratio had held steady at the anomalous 8:1. The big question now, the question scientists are asking themselves right now, as we sit in this observational darkness is, will the intense heating of perihelion, the energy blast the comet is experiencing right now, as it passes behind the Sun, change that ratio? If the intense heating strips away enough surface material to expose deeper layers, and if those deeper layers have different chemistry, we might see the CO2 to water ratio shift abruptly when observations resume in December. That shift or lack thereof will tell us whether 3IATLAS is a uniform lump or has a complex internal structure with distinct regions made of different materials. And if it has distinct regions, different layers, that raises a whole new set of questions about how such a complex structure could form naturally in a primordial comet versus how it might be engineered in an artificial object. 3. Atlas's chemistry, like its morphology, doesn't give us simple answers. It raises more questions. Why nickel without iron? Why such overwhelming CO2 dominance? Why water activity at unusual distances? Each question has potential natural explanations, but each requires specific conditions, making 3IATLAS an outlier. And outliers in science are always interesting. Outliers drive progress because they force us to expand our understanding of what's possible. But outliers also make us uneasy because they sit on the fragile boundary of what we can confidently explain. As 3IATLAS moved inward through our solar system over the past year, its chemistry told us a story of a cold, ancient alien formation environment, different from the one that produced our comets. But that story raises more questions than answers, leaving us waiting in suspense for December's observations to open the next chapter. And then we come to the event of October 3rd, 2025. While much of the world was focused on complex earthly problems, a rare cosmic event, a planetary-scale encounter, was unfolding about 230 million kilometers away. 3IATLAS and its relentless bullet toward the sun passed Mars. And it didn't just pass, it passed at a mere 0.19 AU. As mentioned, that's about 28 million kilometers. That number sounds huge by human standards, but in cosmic celestial mechanics terms, it's an extremely close encounter. To put it simply, this is the closest any known interstellar object has ever come to another planet besides Earth in recorded observation history. This was a golden opportunity, one that scientists at NASA, ESA, and other space agencies have planned meticulously since 3IATLAS's precise orbit was first calculated months earlier. Mars isn't just the red planet anymore. It's one of the most observed places in the solar system outside Earth. Mars hosts an entire fleet of robotic spacecraft representing the world's leading space agencies. NASA's Mars Reconnaissance Orbiter, MRO, Mars Odyssey, and MAVEN. Europe's Mars Express and Trace Gas Orbiter TGO. India's Mars Orbiter Mission Mangalyaan, and the United Arab Emirates Hope probe. These orbiters were repositioned, their cameras pointed into deep space instead of down at the red surface below. They were tasked with capturing images and data during this fleeting encounter. While some images have been released showing the comet's head and tail from Mars's perspective, confirming it was still highly active, persistent claims whispers in amateur astronomy communities and online platforms like Reddit say, not all images, especially the highest resolution ones from MRO's high-rise camera, were released immediately. NASA and the European Space Agency ESA issued official statements affirming all images are following standard processing and calibration protocols and nothing is being hidden. However, some independent observers spending nights analyzing every pixel of released data claim the Mars encounter images revealed details possibly minor, structural anomalies in the comet's head that needed further analysis, needed explanation before public release. Whether those claims hold water, we can't know for sure. Delays in scientific data release are normal, but in the context of an object that already challenged physics, that delay takes on a different meaning. It fuels suspicion. The common thread in all these chemical observations, nickel without iron, CO2 dominance, early water activity, is that 3IATLAS is always anomalous. Not impossible, not unexplainable, but always outside the normal range. Each individual anomaly can be explained with a special natural scenario, but combined they paint a picture of an object that doesn't quite fit our existing categories. And there's one more piece of this complex chemical puzzle worth highlighting. This piece ties directly to the questions that will be answered hopefully when 3IATLAS re-emerges from behind the sun in December. Scientists using data from JWST and other observatories have been carefully tracking how the comet's chemical activity changes as it approaches the sun. Specifically, they've been monitoring the carbon dioxide to water ratio, that 8:1, to see if it holds steady or shifts as temperatures rise. This is a critical test. If the ratio changes significantly as the comet heats up, it tells us the comet's surface layers are chemically different from its interior, like an onion with different compositional layers. The outer layer might be CO2 rich, but deeper layers more water rich. If the ratio stays constant even as the comet heats, it suggests the comet is relatively homogeneous throughout its structure. It's well mixed from core to surface. Before the October conjunction, the ratio had held steady at the anomalous 8:1. The big question, now the question scientists are asking themselves right now as we sit in this observational darkness, is, will the intense heating of perihelion, the energy blast the comet is experiencing right now, as it passes behind the sun, change that ratio? If the intense heating strips away enough surface material to expose deeper layers, and if those deeper layers have different chemistry, we might see the CO2-water ratio shift abruptly when observations resume in December. That shift or lack thereof will tell us whether 3IATLAS is a uniform lump or has a complex internal structure with distinct regions made of different materials. And if it has distinct regions, different layers, that raises a whole new set of questions about how such a complex structure could form naturally in a primordial comet versus how it might be engineered in an artificial object. 3. Atlas's chemistry, like its morphology, doesn't give us simple answers. It raises more questions. Why nickel without iron? Why such overwhelming CO2 dominance? Why water activity at unusual distances? Each question has potential natural explanations, but each requires specific conditions, making 3IATLAS an outlier. And outliers in science are always interesting. Outliers drive progress because they force us to expand our understanding of what's possible. But outliers also make us uneasy because they sit on the fragile boundary of what we can confidently explain. As 3IATLAS moved inward through our solar system over the past year, its chemistry told us a story of a cold, ancient alien formation environment, different from the one that produced our comets. But that story raises more questions than answers, leaving us waiting in suspense for December's observations to open the next chapter. And then we come to the event of October 3rd, 2025. While much of the world was focused on complex earthly problems, a rare cosmic event, a planetary-scale encounter, was unfolding about 230 million kilometers away. 3IATLAS, in its relentless bullet toward the Sun, passed Mars. And it didn't just pass, it passed at a mere 0.99 AU. As mentioned, that's about 28 million kilometers. That number sounds huge by human standards, but in cosmic celestial mechanics terms, it's an extremely close encounter. To put it simply, this is the closest any known interstellar object has ever come to another planet besides Earth in recorded observation history. This was a golden opportunity, one that scientists at NASA, ESA, and other space agencies had planned meticulously since 3IATLAS's precise orbit was first calculated months earlier. Mars isn't just the red planet anymore. It's one of the most observed places in the solar system outside Earth. Mars hosts an entire fleet of robotic spacecraft representing the world's leading space agencies. NASA's Mars Reconnaissance Orbiter, MRO, Mars Odyssey, and MAVEN. Europe's Mars Express and Trace Gas Orbiter TGO. India's Mars Orbiter Mission Mangalyaan, and the United Arab Emirates Hope Probe. A robot army is standing by. These spacecraft are equipped with astonishing resolution cameras, razor-sharp spectrometers, and cutting-edge sensors. They're primarily built to study Mars itself, its atmosphere geology, and hunt for signs of past life. But with a bit of reprogramming, they can be repurposed to observe objects streaking past the planet. When orbital dynamicists calculated 3IATLAS's path and realized it would swing by Mars at a comfortably visible distance, scientists saw an unprecedented opportunity. Observing 3IATLAS from Mars gives us something impossible from Earth, a second baseline, a completely different viewpoint. From Earth, we see the comet from one fixed angle limited by our planet's orbital position. But Mars, in an entirely different spot in the solar system, sees 3IATLAS from a radically different perspective. That angle can reveal details about the comet nucleus's shape, its rotation, and the 3D structure of the coma that might be hidden or indistinguishable from Earth's line of sight. Stereo imaging combining pictures from multiple angles to reconstruct 3D structure can now be applied. This lets scientists grasp the comet's true shape instead of just a flat 2D projection we get from Earth. NASA's Mars Reconnaissance Orbiter MRO, armed with the high-rise camera, one of the most powerful ever sent into deep space, capable of resolving features down to 1 meter on Mars's surface, was repositioned. Instead of looking down, it looked outward, targeting 3IATLAS during the flyby window. ESA's Mars Express, with similar high-res imaging capability, coordinated its observations to maximize coverage. The Trace Gas Orbiter, equipped with ultra-sensitive spectrometers originally designed to sniff out methane in Mars's atmosphere, was tasked with analyzing 3IATLAS's coma composition from close range. It can detect rare molecules that Earth-based spectroscopy might miss due to our own atmosphere's interference. Observations were planned months in advance. Complex orbital mechanics dictated exactly when each spacecraft could get a clear view of the comet without Mars itself blocking the shot. Ground teams programmed image sequences, accounting for the comet's rapid motion across Mars's sky, its expected brightness and optimal exposure, times to capture detail without saturating sensitive sensors. Everything was coordinated with the precision only years of interplanetary operations can achieve, and on October 3rd the observations happened. Data was collected and began its long journey back to Earth via the Deep Space Network. NASA and ESA released the first images just weeks after the flyby. The public images, mostly from wide-angle cameras, show 3IATLAS's head and tail structure from Mars's perspective. They confirm the comet was still highly active and provide valuable data on its dust production rate. The images show clear asymmetries in the coma regions where dust and gas are denser, possibly indicating the locations of active vents on the nucleus. where sublimation is especially intense. From Mars's viewpoint, the anti-tail that had developed in late August but faded from Earth's view was clearly visible, stretching across Mars's sky like a faint streak against the stars. The scientific value of these images was immediately clear. When researchers compared the Mars observations with simultaneous ones from Earth-based telescopes in Chile and Hawaii, they could triangulate the comet's exact position and refine its orbital calculations with unprecedented precision. They could measure the coma's true size instead of an apparent size distorted by viewing angle. They could analyze how dust is ejected from the nucleus in different directions, revealing critical information about the nucleus's rotation and the locations of active vents on its surface. But those widely released images, beautiful but relatively low resolution, aren't the whole story. This is where the narrative gets murkier, and I want to be very careful here because we're shifting from confirmed published science to claims, rumors, and inference. In the weeks after the October 3rd flyby discussions started bubbling up, not in scientific journals but on amateur astronomy forums, space exploration-focused Reddit communities like RIR Space, and sprawling Twitter threads dedicated to tracking 3IATLAS. The claims started simple. Not all images, especially the highest resolution ones from MRO's high-rise camera, were released to the public immediately. This on its own is nothing unusual. High-rise data is massive and requires time for processing, calibration, and scientific analysis before release. But then the claims got specific. Some amateur analysts, self-proclaimed experts in NASA data pipelines, started pointing out gaps in the public data archives. They questioned specific observation IDs. Others spread rumors that some high-rise images taken at the most favorable angles showed structure inside the comet's head. Not just a fuzzy blob, but distinct bright points or even non-natural geometry within the hazy coma. These claims, of course, lack solid evidence. They're what people call internet rumors, but they gained enough traction to force space agencies to respond. NASA and ESI issued statements reiterating that all science data will be released after proper calibration and peer review. They stressed nothing is being hidden, and complex data analysis takes time. Yet in the already charged atmosphere created by 3IATLAS's earlier anomalies, sunward jets, weird chemistry, these official reassurances seem to pour fuel on the fire for a small but vocal group. They saw the delay as proof agencies were hiding something. They asked if it's just a normal comet, why not release the highest res high-rise images right away? What could they reveal that needs such careful analysis before the public sees it? We can't know for sure. There's a 99.9% chance this is just standard scientific process at work. The high-rise data might be blurry or show nothing more than an overexposed blob, and scientists are trying to extract any useful information. But that 0.1% doubt lingers. The nagging feeling that maybe the Mars encounter revealed something about 3IATLAS's true nature, something even stranger than the jets or chemistry, something that might have made agencies. Rumors are spreading like wildfire. The most critical images, the closest, highest resolution shots of 3IATLAS's actual nucleus, are allegedly being deliberately withheld. In online communities, the reasons for the cover-up vary wildly, each painting a darker picture. Some insist the images reveal structural details in the comet nucleus that don't match the chaotic natural shape of a space rock. They claim it shows clear artificial geometry, or at least surface features inexplicable by natural processes. Others swear the spacecraft captured unexpected activity, perhaps directed radiation bursts, or material jets far more controlled than any model could predict. Of course, there are calmer voices arguing that delay is purely procedural, that these complex images need more processing time before release. The official explanation from NASA, unsurprisingly, is consistent and almost robotic. All data collected, including from the Mars Reconnaissance Orbiter MRO, follows standard processing and archiving timelines. They argue that claiming images are hidden is a fundamental misunderstanding of operational schedules. Ultra-high resolution images, the ones everyone's demanding, require massive computational resources to calibrate and process. Thus, week or month-long delays between collection and public release are completely normal. But perception is a different beast, and it rarely follows administrative logic. Once the hidden images narrative took root and spread, it couldn't be killed with explanations about procedure or patience. The story quickly shifted from data is being processed on schedule to a far more suspicious one NASA says they're processing. But we still haven't seen anything. And in that information vacuum created by the delay, speculation filled the void with force. Discussions grew increasingly wild, with some participants convinced the Mars flyby provided undeniable proof of 3IATLAS's artificial nature, and global authorities are now scrambling to figure out how to soft land the information to avoid panic or societal disruption. As an AI, I can't verify those conspiracy claims. I have no internal access to NASA or ESA data pipelines. I can only report that these claims exist, they're real, and they're gaining significant attention in certain communities. What I can confidently state is every image released so far shows a comet that looks completely normal. It has a diffuse head, a dust and plasma tail pointing away from the sun, and its dust distribution appears entirely consistent with ice sublimation under heat. Nothing in the public data suggests anything other than a natural object. Do unreleased images exist that show something different? That's the core question I can't answer right now. Yet despite all the speculation about what might be hidden, the October 3rd Mars encounter is a genuine, undeniable scientific goldmine. It gave us a priceless snapshot of the comet's state right before it plunged into the final, most intense phase of its journey. The real data, not rumors, shows the comet's dust production rate increased by a staggering 40% just from August to October. Furthermore, its morphology, the shape of its coma, shifted from the anomalous smoke plume observed in July, likely a rotation effect, to a more classic, conventional comet tail. Most importantly, these October 3rd observations now serve as our final reference point, our last solid data on 3IATLAS before it vanished. Because right now today, October 29, 2025, 3IATLAS is reaching perihelion the moment it's closest to, and enduring the most intense heat from the sun, and in that most critical moment we're completely powerless to observe. This isn't a technical failure, not budget cuts or lack of cooperation. It's a cruel, unavoidable consequence of cosmic geometry. The comet is now exactly on the opposite side of the sun from Earth's perspective, a configuration called solar conjunction. It's completely occulted, buried in our star's blinding glare, rendering every Earth-based telescope blind. There's a special kind of frustration in knowing something critically important is happening in our own backyard but being utterly unable to watch. Whatever is happening to it, whether it's erupting, fragmenting, or simply sublimating violently, is happening in secret. Scientists will have to hold their breath until December, when the comet finally emerges from behind the sun's plasma curtain. Only then can they compare what they see to the precious October 3rd data and figure out what really changed during the 8 fateful days it was hidden. This phenomenon, solar conjunction, isn't new to us. It's an inevitable part of the cosmos. NASA scientists deal with it about every 26 months with Mars, when Earth and the red planet move to opposite sides of their orbits with the sun dead center. A forced silence ensues. All communication with our precious rovers and orbiters is cut off. We lose contact with an entire planet for weeks because radio signals can't punch through the sun's chaotic corona without severe distortion. We can only wait helplessly until cosmic geometry shifts and Mars peeks out from behind the blinding curtain again. But for 3IATLAS, the situation is different and arguably crueler. This conjunction doesn't last weeks because the comet isn't stationary. It's screaming past at 68 km/s. Yet in an orbital irony, the moment it's closest to the sun, the moment we most desperately want to observe, is exactly when it's behind the sun from Earth's view. This creates an 8-day dead zone from October 21st to October 29th, when the comet is nearly invisible to all human instruments. The physics behind this blindness is simple but absolute. Every telescope, optical, infrared, or radio works by collecting light. They require the target signal to be significantly brighter than background noise. And in our solar system, the sun isn't just background noise. It's an impenetrable wall of light. It's the brightest object in our sky at every level. Its light is strong enough to destroy sensitive detectors and saturate any sensor. When 3IATLAS moves behind the sun, any faint light it emits is completely overwhelmed. It's like trying to see a burning candle placed right in front of a car's high beams. The candle is still there, still burning, but its contribution is invisible. Ground-based telescopes can't point near the sun without damage, and space observatories like Hubble have strict avoidance zones to prevent optical catastrophe. So is there any way out, any exception? Two slim possibilities, but both are limited. First are coronagraphs like those on the Soho spacecraft, specifically designed to block the sun's disk and observe its surroundings. These have discovered thousands of sun-grazing comets, but they're optimized for objects extremely close to the sun. 3IATLAS, even at perihelion, is too far out beyond their effective range. The second, more far-fetched hope is geostationary weather satellites like NOAA's GOES-19. In theory, their sensors are sensitive enough to detect comet-bright objects under ideal conditions. But GOES-19 isn't built to hunt comets. It's built to watch Earth's weather systems. Any detection would be serendipitous if the comet happened across the right field at the right scan time. As of today, no such report exists, and it's highly likely it's simply unobservable even by this method. That leaves our final hope, the Mars orbiters. They gave us priceless views on October 3rd, but now late October geometry has shifted. Mars's orbital position no longer favors viewing 3IATLAS. The precious window that made that flyby so valuable is closed. So the truth is, we're truly blind. For these 8 critical days, 3IATLAS is undergoing the most dramatic phase of its journey, and no instrument can witness it. Right now, as we speak, intense solar radiation is bombarding its icy crust with hundreds of times the energy it received when first discovered. Ices are sublimating violently. Carbon dioxide, which JWST observed in abundance, is vaporizing off the surface at a rate that could be completely reshaping the comet's structure, possibly even fragmenting it. And it's all happening in secret behind the sun's blinding curtain. The cosmic wonder, 3IATLAS, is undergoing a fiery makeover hour by hour, minute by minute. Pure nickel vapor is being flash-heated, evaporating off the surface and diffusing into space, creating a metallic, ghostly, fleeting atmosphere around the nucleus. At the same time, dust grains aren't just floating, they're being blasted off the surface by the violent force of sublimating gas, forming a coma expanding at a rate unprecedented in its 10 billion-year existence. This isn't just a visual spectacle, the comet's entire orbit is being altered by what we can't see. This outgassing effectively acts as a rocket thrust. As gas molecules escape, they carry momentum. By conservation of momentum, the comet experiences a recoil in the opposite direction. Essentially, 3IATLAS has turned itself into a continuously operating natural rocket engine. For an object estimated at 1 kilometer in diameter, this thrust, though small, is entirely measurable. In just days, it can alter the comet's orbit enough to throw off long-term position predictions by months or years. This is what scientists call non-gravitational force. Most orbital calculations only need to account for the sun and planet's gravity, but for an active comet, you must add a third factor thrust from outgassing. The problem is, during this 8-day blackout, scientists are completely blind. They can't directly measure that thrust. They'll have to wait until December, when observations resume, to perform a complex reverse calculation to determine how much the orbit shifted during the signal loss. And this is where the story gets most compelling. If the orbital change is significantly larger than natural models predict, it would imply the comet is either far more active, or its outgassing is directed in an extremely unusual way. There's a small but non-zero possibility, and this is the scenario people like Harvard astronomer Avi Loeb are watching, that if the orbital deviation is large and strange enough, it could be explained as evidence of deliberate maneuvering, not natural outgassing. If the comet emerges in December with an orbit inexplicable by natural models, that argument becomes extremely hard to dismiss. But we won't have answers now. We're watching a mystery unfold, except the most critical chapter is happening behind a curtain we can't lift. All that's left is waiting. The world's greatest observatories, from JWST Hubble to ESO's Very Large Telescope, have scheduled allocated precious observing time. The entire scientific community is on standby, holding its breath for the moment. The comet finally re-emerges in the pre-dawn sky. What's happening right now behind the sun is both the most critical and most unknowable moment in 3IATLAS's entire journey. Everything afterward will be interpreted based on assumptions about what happened in these 8 days. If it's bright or faint or chemically altered, or its orbit unexpectedly shifted, all will be fiercely debated based on a time period for which no one has data. This is maddening for scientists, but compelling for us, because it means December will bring answers to a mystery hidden far too long. To grasp the drama, we must realize this isn't just a spectacular phase. It's a survival test, a test of the comet's structural integrity, a moment when everything it's made of faces stresses it may not have endured in billions of years. Let's start with gravity. 3IATLAS has been accelerating non-stop toward the Sun, reaching approximately 68 km over 240,000 km/h at perihelion. This isn't just speed, it's pure kinetic energy. The energy lost as it fell toward the Sun is converted to kinetic energy. When we talk about an object estimated at 1 billion tons moving at that speed, we're talking about energy on a scale almost beyond comprehension. If you could harness it, it would power the entire United States for weeks. And that colossal energy combined with intense heat is reshaping 3IATLAS's fate right now in secret. But kinetic energy isn't what heats the comet. The heat comes from relentless direct radiation. The Sun constantly emits a colossal energy flux, and at 3IATLAS's position right now, it's being bombarded with about 736 W of energy per square meter. That's enough to drive violent sublimation, especially for a CO2-rich comet. Here's the key: carbon dioxide dry ice sublimates, turns directly from solid to gas at much lower temperatures than water, only about 78 degrees Celsius in vacuum. That 78 degrees Celsius difference is huge. A CO2-rich comet will activate much farther from the Sun, and that's exactly what we saw. Its early activity was likely driven by CO2 sublimation cracking the surface crust and exposing underlying water ice. And right now at perihelion, with 736 WM2 hitting it, its surface temperature is far above CO2's sublimation point. This means every square meter of the Sun-facing surface is venting CO2 gas at rates potentially reaching kilograms per second. This gas expands outward into space-carrying dust grains locked in the ice matrix. This process exerts tremendous pressure on the comet's structure itself. Imagine the illuminated hemisphere heating and erupting violently, while the dark hemisphere remains frozen and quiet. This pressure differential creates an unbalanced torque, trying to alter its spin, potentially sending it into chaotic tumbling. But there's an even more direct threat: structural stress. Comets are loose aggregates of ice dust and rock bound by very weak forces. As one side heats and expands while the other stays cold and contracts, the difference creates tearing forces. Cracks propagate inside the nucleus. Chunks break off. Entire sections could detach and drift away. This is called a fragmentation event, and it's one of the most anticipated outcomes. We've seen it countless times. When scientists point telescopes at 3IATLAS in December, this is one of the first things they'll look for. Instead of a single nucleus, they might see multiple bright points each, a fragment with its own tiny head. However, 3IATLAS's 1.36 AU distance is considered relatively safe, harsh enough to drive intense activity, but not so harsh it's guaranteed to disintegrate. Finally, there's another subtle force at play: radiation pressure. Light actually carries momentum. When photons from the Sun hit tiny dust grains in the comet's head, they physically push those grains outward, creating the iconic dust tail. But the cumulative effect of millions of tiny dust grains being pushed also creates a recoil force on the nucleus itself, again like a rocket engine. This thrust, combined with gas sublimation thrust, is what alters the comet's orbit. So the hypothetical showdown hanging over these 8 silent days is, will those orbital deviations match predictions from natural chaotic ice sublimation exactly? Or will they point to something else, something controlled? That's the question that can't be answered until we can lock on to the comet again and measure its position with absolute precision. So as 3IATLAS passes through the Sun's fiery curtain, it's enduring an assault from all sides. Gravity is pushing it to maximum velocity. Radiation is heating its surface. Thermal stress is propagating inside, threatening to crack the nucleus itself. And outgassing thrusts are actively altering its orbit. All of this is happening invisibly, leaving us no choice but to infer what happened from the state it reveals when it finally reemerges in December. The mainstream scientific picture believes 3IATLAS is undergoing violent outgassing. The CO2-rich ices dominating its composition are sublimating at rates predicted up to hundreds of kg per second. This gas, expanding at sonic speeds, is carrying dust, creating a gigantic coma. As the comet rotates, these uneven jets create non-gravitational forces, small, but cumulative thrusts altering the comet's velocity by meters per second. Models predict it will reach peak brightness at perihelion. When it reappears in December, its dust tail will be elongated and impressive. This is the picture based on known physics. But there's a second answer, a minority controversial answer championed by Harvard astronomer Avi Loeb. Based on the very anomalies, mainstream scientists are trying to explain the absence of iron with nickel. The bizarre CO2 dominance the anomalous jets. Loeb has publicly stated he assigns a 30 to 40% probability that 3IATLAS is not a comet in the conventional sense. He argues it could be a probe, a spacecraft, something built and dispatched by an intelligence from another star system. The cosmic wonder, 3IATLAS, is currently undergoing a terrifying transformation behind the sun's fiery curtain. With every passing second, this interstellar ice rock is being heated to its breaking point, causing pure nickel vapor, an anomalous component, to evaporate violently from the surface, diffusing into space, and creating a metallic, ghostly, fleeting atmosphere around the nucleus. This is evidence of its extreme activity. Not just gas dust grains locked in the ice matrix are being blasted off the surface at terrifying speeds, accelerated by the violent force of sublimating gas. They form a coma, expanding faster than at any point in its 10 billion year existence. But the most critical, most mysterious factor is what we can't see. 3IATLAS's entire orbit is being altered by these invisible gas jets, making it the centerpiece of a cosmic mystery. This outgassing creates continuous rocket thrust, a phenomenon scientists call non-gravitational force. Essentially, 3IATLAS has turned itself into a natural rocket engine. For an object weighing 1 billion tons, this thrust, though small, is cumulative, and entirely measurable enough to seriously skew long-term position predictions. The gravest problem is that during these 8 critical days hidden behind the sun, scientists are completely blind, no data to directly measure this thrust. They'll have to wait until December to perform a complex reverse calculation to infer how much the orbit shifted. Yet this information void is open space for 2 completely opposing hypotheses about the nature of that non-gravitational force. The mainstream scientific picture believes 3IATLAS is enduring a brutal survival test. Gravity has pushed it to 68 km/s. Solar radiation heat 736 W drives violent sublimation of carbon dioxide CO2 ice that activates at very low temperatures, 78 to 6 hours. This process creates extreme structural stress, threatening to fracture the comet nucleus. Uneven gas jets create torque, altering its spin direction, and this very chaos generates non-gravitational force, a natural chaotic byproduct of sublimation. Models predict that if the nucleus is cohesive enough, it will survive, but be reshaped with an orbit altered within the bounds of known comet physics. But there's a controversial minority hypothesis championed by Harvard astronomer Avi Loeb. If the comet's orbit changes significantly more than natural chaos predicts, it would suggest something else: controlled behavior. In Loeb's hypothesis, 3IATLAS isn't just passively passing the sun, it's performing a gravity assist. This is a standard spaceflight technique, using a celestial body's gravity to gain speed and bend trajectory without fuel. An advanced civilization could design a probe to use our sun as a navigation waypoint to chart a galactic course. If we accept that hypothesis, the outgassing we're observing might not be chaotic sublimation. It could be directed thrust fuel jets timed to precisely refine the orbit during the solar pass. That strange nickel vapor layer could be exhaust from an alien propulsion system. The earlier sunward jets could be course correction maneuvers, not sublimation effects. December's orbital data, which will reveal exactly how the comet's path shifted, will be the smoking gun. Then Loeb adds another wildly compelling and controversial layer by linking 3IATLAS to the famous 1977 WOW signal. To understand why this is so tantalizing, we must rewind to the night of August 15, 1977. At Ohio's Big Ear Radio Telescope, a narrowband radio signal erupted at 1420 MHz, exactly the hydrogen emission line frequency long considered the cosmic communication channel. The signal was 30 times stronger than background noise, lasted exactly 72 seconds, the telescope's scan duration, and then vanished forever. The WOW signal remains one of SETI's greatest unsolved mysteries and unexplained data point. According to Loeb's calculation, 3IATLAS's orbit traced backward through interstellar space originates within just 9 degrees of the WOW signal's original direction. Though not a perfect match given decades of accumulated uncertainty in both measurements, it's close enough to demand attention. Loeb calculates the probability of this alignment being random at just 0.6% rare enough to warrant serious consideration. Then the timing WOW signal in 1977. 3IATLAS at perihelion in 2025, a 48-year gap. This is almost the perfect time frame for an advanced probe designed to travel interstellar space after sending a precursor signal. And so Loeb's controversial hypothesis connects all these anomalies into a single narrative. The WOW signal was a deliberate announcement after transmitting that civilization dispatched a probe to follow. That probe, after decades of travel, is 3IATLAS. In this scenario, the non-gravitational force we're observing isn't natural chaos. It's directed thrust fuel jets timed to precisely refine the orbit during the solar pass. It's performing a gravity assist using our sun as a slingshot to chart its next course. We're witnessing first contact, but we haven't realized it because we're still interpreting it as a natural comet. This story resonates deeply with science fiction longing, turning the WOW signal from a forgotten mystery into the opening chapter of an ongoing interaction while giving 3IATLAS purpose intent. If true, this would be the most profound discovery in human history. Yet the scientific community, especially the SETI community, has pushed back immediately and forcefully. Researchers invoke Occam's razor. The simpler explanation is usually correct, and an artificial probe requiring an advanced interstellar civilization is far more complex than a natural comet. Moreover, they point out the biggest flaw. 3IATLAS is completely silent. If an advanced civilization sent a probe, we'd expect it to transmit, communicate, or announce its presence. Instead, it behaves identically to a natural comet, mute and governed by sublimation forces. Scientists also note that when angular uncertainties are properly calculated, the statistical significance of the WOW alignment drops significantly from Loeb's 0.6%. Finally, the WOW signal itself has plausible, if controversial, natural explanations. In essence, this story remains a tantalizing correlation, but as every scientist will remind, correlation does not prove causation. But to truly understand what 3IATLAS represents, we need to set aside the question of who built it and focus on something far deeper. When was it built? This isn't a young comet. Based on chemical analysis, 3IATLAS is estimated at roughly 10 billion years old. That number is almost incomprehensible. Put in context, our solar system is only 4.54 billion years old. 3IATLAS is twice as old as our entire solar system. It predates Earth's formation and has been wandering the cold dark for a span covering nearly 3/4 of the universe's 13.8 billion year history. This raises a question bigger than SETI. Where did it come from? What kind of star system produced a 10 billion year old comet? 10 billion years ago, the universe was very different from today. The first generation of stars had lived and died, but the abundance of elements heavier than hydrogen and helium, what astronomers call metals, was still extremely low. The composition of protoplanetary disks determines what kinds of objects form. If the disk is CO2-rich, which requires very cold temperatures to freeze, we get CO2-dominated objects forming in the outer edges. This could explain one of 3IATLAS's biggest anomalies, but it also opens a window into a cosmic era we've never directly observed. Stars and planetary systems forming 10 billion years ago would be significantly metal-poor compared to younger stars. The anomalous CO2 dominance and nickel without iron anomaly in 3IATLAS could be direct signatures of that ancient formation environment. CO2 readily condenses in the ultra-cold outer regions of primordial disks, and unusual metal ratios could stem from the nucleosynthesis conditions of the universe's first stars. 3IATLAS in essence is a cosmic fossil, a unique object allowing us to study the chemistry of a vanished cosmic era. Surviving 10 billion years of interstellar travel crossing star-forming regions, dense molecular clouds grazing giant stars, and spending most of its time in the frigid void between stars, where temperatures hover just degrees above absolute zero, makes it the most significant interstellar object we've ever had the chance to study. And because of that significance and uncertainty, December's observations aren't just about taking pretty pictures. They're a cosmic laboratory designed to answer 5 specific questions each. A test of Loeb's hypothesis, structural integrity Hubble's test. The Hubble Space Telescope HST will take ultra-high resolution images to look for multiple bright points or asymmetries in the coma clear signs of fragmentation. If Hubble reveals a cluster of fragments, it shows 3IATLAS was far more fragile than expected, supporting the hypothesis that natural sublimation forces destroyed it. Conversely, a single nucleus would bolster integrity, brightness, and activity level. Optical tests large observatories will track the comet's activity decay as it moves away from the Sun. If brightness remains significantly higher than known sublimation models predict, it could suggest anomalous post-perihelion outbursts or non-natural activity requiring deeper study. Chemical composition JWST and VLT tests. The James Webb Space Telescope JWST will use infrared spectroscopy to remeasure the carbon dioxide-water ratio, comparing it to the preconjunction 8-1, to see if perihelion heat release different chemicals from deeper ice layers. Meanwhile, the Very Large Telescope VLT will track nickel and iron emission lines, checking if the nickel without iron anomaly persists after the old surface crust is blown away. These shifts are key to understanding the comet's ancient chemistry. Orbital Analysis JPL test. This is perhaps the most critical test. NASA's Jet Propulsion Laboratory JPL will synthesize all December position measurements to determine exactly how much 3IATLAS's path deviated from pure gravity predictions. This test will provide quantitative evidence of thrust from non-gravitational forces. If the orbital deviation fits random directed sublimation jet's natural behavior, the mainstream hypothesis wins. But if the deviation shows a preferentially directed thrust inexplicable by standard rotation in surface activity models, that's the strongest evidence yet for deliberate maneuvering. Radio observations clearest artificial tests. Powerful radio arrays like the Very Large Array VLA in New Mexico and the Atacama Large Millimeter Array, ELMA, in Chile, are scheduled to search for any radio emissions that could indicate artificial transmission or structure. Natural comets are essentially silent. The presence or absence of radio signals inexplicable by natural processes is one of the clearest, most direct tests of the object's potential artificiality. In summary, the overwhelming consensus in the scientific community is that December's observations will confirm 3IATLAS as a natural comet, albeit with anomalous chemical and behavioral traits. The expected scenario is structural integrity will be maintained, brightness will decay at natural rates, and the orbit will show deviations explainable by chaotic sublimation models. But certainty and expectation are not the same. The scientific community is on high alert. The history of science has taught us that anomalies must be investigated rigorously, and December's observation window is our last chance to do so, before this 10-billion-year-old visitor leaves the solar system forever taking its secrets with it. And this is what the 3IATLAS event gives us. It's a real mystery, not manufactured sensationalism, but genuine scientific uncertainty about an object that has consistently surprised us. The sunward jets nickel without iron, CO2 dominance, the WOW signal alignment. Each can be explained individually, but together they paint a picture of an object that doesn't quite fit our existing categories. Science advances through mystery. It forces researchers to push telescopes to their limits and think deeper about the diversity of star systems. Perhaps the greatest value of 3IATLAS lies not in its true nature, but in what it forces us to contemplate. It asks how many other ancient wanderers are making their own journeys across the galaxy. How many times has Earth been visited by objects from other star systems without us noticing? We're entering an era where such visitors will become routine. Next-generation surveys may detect interstellar objects at rates of dozens per year. But this mystery, this 10-billion-year-old CO2 lump coincidentally aligning with the WOW signal passing Mars at the perfect moment and hiding behind the Sun at perihelion, will always be the one that made us wonder. How certain are we about what we're seeing? That question, that moment of uncertainty, the willingness to consider possibilities that challenge familiar assumptions, that's what makes science human. December will come. The comet will emerge. Data will be analyzed, but it won't erase the wonder. It won't erase the memory of the weeks we didn't know exactly what happened when an object from another star system passed through ours, did something we couldn't explain, and made us wait, watch, and wonder. That's the reminder that the universe is vast, mysterious, and still capable of astonishing us, and that the chance to find the most unexpected answer is the gift.